In this video, let me consider maximum power transfer theorem, its statement and its proof. Let's see what is the statement of maximum power transfer theorem. This theorem states that in any active network, maximum power delivered to the load takes place when load impedance is equals to the complex conjugate of the network impedance. Now let me consider one circuit. So in this circuit, Eg is the supply voltage. Let Zg is impedance of the network. Let Zg is impedance of the network or circuit, and let ZL is load impedance of network. We'll assume that the terminal, this is A and this is B. At terminal A and B, a load resistor or load impedance ZL is connected. So according to the maximum power transfer theorem, the maximum power will be delivered to load, that is ZL, when ZL is equal to complex conjugate of Zg, that is ZL is equal to Zg star. It means complex conjugate of ZL. That is, suppose the network impedance is say 5 plus J3. So in that case, the ZL should be complex conjugate of Zg. So in this case, Zg is equal to 5 plus J3. So in this case, if I choose ZL is equal to complex conjugate of this, that is 5 minus J3, then the maximum power will be delivered to ZL. This is the statement of maximum power transfer theorem. Suppose the network impedance, that is Zg, is not a complex number, that is suppose Zg is equal to 5. In that case, ZL value supposed to be 5, so that the maximum power will be delivered to the load. Let me consider one simple example so that we can easily understand. Let me consider one simple example. Say this is terminal A and this is B. We'll assume that this is the load resistor RL, and let me consider the value of network impedance is say 5. So here now we'll see for what value of RL the maximum power will be delivered to RL. Now let me assume say RL is equal to 1 ohm. So if I consider RL is equal to 1 ohm, let me find current in the circuit. Let I is the current in the circuit. In that case, let me write current I is equal to V by R, that is 5, that is 10 divided by 5 plus 1 is 6. So I value will be 1.667. Suppose if I calculate the power delivered to load RL, the formula is P is equal to I square into RL. So here I value is 1.667 square into RL value is 1. So it gives the power as 2.778. Now let me take the load resistance value, say RL is equal to 2 ohm. Let me take 2 ohm. Now the current in the circuit will be I is equal to 10 divided by 5 plus 2, that is 7. The value of this will be 1.428. Now let me calculate the power delivered to load RL when RL is equal to 2 ohm, that is P is equal to I square into RL, that is 1.428 square into 2. It gives 4.08 watt. Similarly, now let me consider RL value is equal to 3 ohm. If I consider 3 ohm, the current in the circuit will be I is equal to 10 divided by 5 plus 3, that is 8. The current will be 1.25. If I calculate the power, it gives 1.25 square into 3, it gives 4.68 watt. Similarly, if I consider RL equal to 4 ohm, let me take it as 4 ohm, the current will be I is equal to 10 divided by 5 plus 4, 9. Its value is 1.11. The power will be 1.11 square into 4. It gives 4.93 watt. Similarly, if I consider RL equal to 5 ohm, let me take it as 5 ohm. Now current I will be equal to 10 divided by 5 plus 5 is 10. The current is 1 amp. The power will be 1 square into 5. So now the power will be 5 watt. Now consider RL equal to 6 ohm. I'll take it as 6 ohm. So in this case the current will be I is equal to 10 divided by 5 plus 6 is 11, which is equal to 0.909. So the power will be 4.95 watt. Let me take last value, RL equal to 7 ohm. The current will be, I'll make it a 7 ohm. The current will be equal to 10 divided by 5 plus 7 is 12. That is 10 by 12, it gives 0.8333. Now the power will be 4.86 watt. So now here we can observe that when the value of resistance is 1 ohm, the power was 2.778. Similarly for 2 ohm, its value is 4.08. So the value is increasing here. So when the RL value is same as 5, so for this case we can see that the maximum power is delivered. That is, when RL is equal to 5, we when RL is equal to 5, we got maximum power. So here the power is maximum. So we can conclude that the maximum power will be delivered to the load when load impedance is same as network impedance. So in this case, the load impedance is, network impedance is 5. So the load impedance supposed to be 5, so that maximum power will be delivered. Similarly, if we keep on increase the load value, which is greater than network impedance, in that case also the power will be decreasing. So only for RL equal to 5 we received maximum power. Now we consider the case where load is made of only resistor. So we'll consider the first case, that is load is pure resistive. Let me draw the circuit here. Let EG the supply voltage. So this is the terminal, say A and B. To terminal A and B, a load is connected which is made of only resistor. Let me call this as RL, which acts as a load, which is nothing but load. Here we know that this is network impedance, that is ZZ, which is nothing but RG and JXG. Let I is the current flowing into the circuit. So now in this circuit, we'll calculate the total impedance of the circuit. That is, total impedance of the circuit is ZG plus RL, which is nothing but RG plus RL plus JXG. This is total impedance of the network. Now let me find the current. We know that current is equal to supply voltage divided by total impedance, that is EG divided by total impedance, RG plus RL plus JXG. Let me calculate the magnitude of the current, that is I is equal to under root Eg square divided by Rg plus RL square plus Xg square. I can represent it as I is equal to, here Eg square and square root will get cancelled. On numerator will get only Eg divided by denominator will be as it is, that is Rg plus RL square plus Xg square. Now we'll see what is power delivered to the load. Therefore, power delivered to the load is equal to current square into RL. So here current is nothing but this equation. Therefore, I can write P is equal to current square, that is square of this, that is Eg square divided by. So if you take the square of this square root will get cancelled. On denominator will get Rg plus RL whole square plus Xg square into this RL is kept as it is. I will call this as equation 1. So now we are supposed to calculate for what value of RL the maximum power will be delivered to the load. So maximum power will be delivered to the load. The condition for that is maximum power will be delivered to the load for the condition that is we supposed to differentiate power with respect to the variable. Here the variable is resistance because RL is the variable. Therefore, dP by dRL it should be equal to 0. So this is nothing but differentiation of equation 1 with respect to RL, that is d by dRL. Now let me write the equation 1, that is power Eg square into RL divided by this term, that is Eg square into RL divided by Rg plus RL whole square plus Xg square and equated to 0. Now we'll differentiate this using U by V rule. So in that case I will keep denominator as it is, that is Rg plus RL whole square plus Xg square. This is the denominator, I will keep it as it is. Differentiation of numerator with respect to RL. Here Eg square is constant. So differentiation of RL with respect to RL is 1 minus, now keep numerator as it is, that is Eg square into RL into differentiation of denominator. It with respect to RL it gives 2 Rg plus RL. And we know that as per formula the denominator square. So anyhow it is equating to 0. The denominator when it goes to right hand side it will become 0. So I will ignore that. So here we can see that Eg square is common in both the side. I can write Eg square, I'll take it as common. So here the first term will be Rg plus RL whole square plus Xg square minus, here Eg square I will take out, RL into 2 Rg plus RL is equal to 0. Now if I take Eg square on right hand side it will become 0. So that I can write Rg plus RL whole square plus Xg square minus RL into 2 Rg plus RL is equal to. So further I will simplify this. I will open the bracket here. It is of form x plus y whole square, that is Rg square plus RL square plus 2 Rg into RL plus Xg square minus, here we have 2RL into Rg plus 2RL square is equal to 0. I can write Rg square plus RL square plus 2RgRL plus Xg square minus 2RLRg minus 2RL square is equal to 0. Let me simplify this further here. So here 2RgRL and minus 2RgRL will get cancelled. Here we have RL square and minus 2RL square will get minus RL square. Let me write the remaining terms, that is Rg square. So here RL square minus 2RL square is minus RL square. This and this will get cancelled, plus Xg square is equal to 0, or I can write RL square is equal to Rg square plus, I can write RL is equal to square root of Rg square plus Xg square. So here we can see that the load resistance RL must be equal to square root of Rg square plus Xg square. Then the maximum power will be delivered to the load. Or this can also be represented as RL is equal to magnitude of Zg, because Zg is nothing but Rg plus Jxg. If we take the magnitude, it will become RL equal to magnitude of Zg. Both are correct. So in this case, if we consider Xg equal to 0, then definitely RL will be equal to Rg. That is, if Xg is equal to 0, in that case RL will be equal to Rg. So here in this previous example, we have already taken the same case where in this term the Xg term is 0. So if Xg is 0, then RL will be equal to Rg. So when RL is equal to 5 ohm, the maximum power will be delivered. Therefore, we can conclude that if the load is made of only resistive, then RL should be equal to under root of Rg square plus Xg square, so that the maximum power will be. Now let me consider the second case where this ZL is such that here the resistance is fixed but the reactance is variable. Let that be my second case. Variable. That is, load resistance is fixed but load reactance is variable. Let the load is ZL, which is equal to RL plus JXL, where RL is load resistance which is fixed and XL is load reactance which is variable. Let me draw the same circuit again. So this is the circuit for this condition. Now let me find the total impedance of the circuit. That is, total impedance is equal to Zg plus ZL. That is nothing but Rg plus Jxg plus RL plus Jxl, or I can write it as Rg plus RL plus Jxg plus XL. Now let me find the current in the circuit. Let I is the current flowing in the circuit. I is equal to, we know that Eg divided by total impedance, which is nothing but Rg plus RL plus J Xg plus XL. Now similarly, let me take the impedance, the magnitude of current, that is I is equal to Eg square divided by Rg plus RL square plus Xg plus XL square under root, that is I am taking magnitude. So we are supposed to do squaring and square on the right side. It is nothing but Eg divided by under root. We have Rg plus RL square plus Xg plus XL square. Now the power delivered to the load is given by power delivered to the load is equal to I square into RL. P is equal to I is nothing but Eg square divided by Rg plus RL square plus Xg plus XL square into RL, that is I square into RL. I square is nothing but Eg square divided by this square root and square will get cancelled. We'll get only Rg plus RL whole square plus Xg plus XL whole square into RL. The same thing is written here. That is the maximum power delivered to the load for the condition we are supposed to differentiate this expression with respect to XL, because XL is the variable, that is dP by dXL equated to 0. That is nothing but d by dXL. So P is nothing but this entire term, that is Eg square into RL divided by Rg plus RL square plus Xg plus XL square equated to 0. Now let me differentiate this. Again, applying by U by V rule, I'll keep denominator as it is, Rg plus RL whole square plus Xg plus XL whole square. Differentiation of numerator with respect to XL is 0 because there is no XL term here, minus, now I'll keep numerator as it is, that is Eg square into RL. I will try to differentiate the denominator with respect to XL. So the first term will be 0. So with respect to second term, differentiating second term with respect to XL, it gives 2xg plus XL, which is equal to 0. Anyhow, denominator will become 0, so I will ignore that. Simplifying this further, so this term will be 0 minus, this can be written as Eg square into RL 2xg plus 2xl is equal to 0. So let me simplify this here. So here I can write this as, it is same as Eg square into RL 2xg plus 2xl is equal to 0. If I take this Eg square on right hand side, again it will become 0. Then on left hand side we'll get 2RL into xg plus 2RL into XL is equal to 0, or I can write xg is equal to minus XL, or I can write XL will be equal to minus xg. So here we can see that the inductive reactance or XL is negative of xg, that is if xg is positive, then XL will be negative, or if xg is negative, then XL will be positive. Thus it is. So here we can see that the reactance of load and the reactance of the network is same, but is of opposite sign. That is, here network reactance and load reactance are of same magnitude, but opposite in sign. It means that if network impedance, it means that if the network reactance is capacitive, then load reactance is inductive, or if network reactance is inductive, then load reactance will be capacitive. We will take case 3 where both XL, that is inductive reactance, and RL, load resistance, are variable. In case 1 only resistance was varying, in case 2 only inductance was varying. In case 3 we will consider both as varying or both are variable. Now as we know, in case 2, when XL alone was variable, the condition for maximum power transfer is XL is equal to minus Xg. That is, as we seen here, XL is equal to minus Xg. If I consider XL is equal to minus Xg in this equation, I will call this as equation A. If I substitute XL equal to minus Xg in this equation, I will get P equal to, the numerator will be Eg square into RL, and denominator will be, here Xg will be equal to minus XL, means this term will become 0. The remaining term is Rg plus RL whole square. So we got this power by considering XL equal to minus Xg. I will call this as P max. Now if we consider RL is also variable, the condition for maximum power is, that is, the maximum power will be obtained if we differentiate this P max with respect to RL. That is, dP max by dRL is equal to 0. Now let me differentiate this P max equation with respect to RL, so that I can get d by dRL. P max value is Eg square into RL divided by, we have Rg plus RL whole square is equal to 0. Now by applying again U by V rule, I can simplify this as, I'll keep denominator as it is, Rg plus RL whole square into differentiation of numerator with respect to RL, it gives Eg square minus, I'll keep numerator as it is, that is Eg square into RL, the differentiation of denominator it gives 2Rg plus RL is equal to 0, or I can simplifying this, I can write Rg plus RL whole square Eg square is equal to Eg square into RL 2Rg plus 2RL, or I can write Rg square plus RL square. I will expand this bracket. 2Rg into RL is equal to, here Eg square will get cancelled, and on right side I can write 2RL Rg into RL plus 2RL square. Further simplifying this, I can write 2Rg RL, and this 2Rg RL will get cancelled, will get Rg square plus RL square is equal to 2RL square, or I can write Rg square is equal to RL square, that is RL square if I take on right side, therefore I can write RL is equal to Rg. So it means that when both XL and RL are variable, the condition for maximum power delivered to the load will be RL is equal to Rg and XL will be equal to minus Xg. So that is nothing but complex conjugate of network impedance, that is load impedance is equal to complex conjugate of network impedance. Thus the maximum power transfer theorem is proved. Thank you for watching.